Hey,
Okay, so I'm just going to, yeah, as viewers settle in, we'll start sharing out the last link. Doo-doo-doo.
apparently 73 people are coming.
Oh my gosh.
There's the Hangout link. Yeah, they've totally changed pages on me. I'm so confused. It's all good. It's all good. Monitor and adjust. That's how we roll here.
That's right.
All right. And we have viewers settling in, so take it away, Andy.
Oh, fantastic. Well, welcome everybody to tonight's. Well, it's our partnership hangout with MyMoon and Cosmoquest. I think most of you probably know what Cosmoquest is. MyMoon you may not be as familiar with. We are a little website that's run out of the Lunar and Planetary Institute in Houston. We're funded by the NASA Science Mission Directorate, and our goal is trying to bring lunar science and exploration to the masses, particularly the masses that it's never really reached before. 18 to 25-year-olds. We are more than welcome to have anybody join us, especially those from the Cosmoquest Circle on Google Plus. The Google Plus is brand new for us. We used a different platform in the past. So I am here trying to learn the ropes of this as fast as I can, and then Cosmoquest will hand everything over to us, and hopefully they'll join us from time to time, however. But in the meantime, they're kind of running the show for us. I'm going to do my best to make sure I'm talking and asking questions this evening so we can keep this thing going and not be boring. Uh, so with us tonight, by the way, I'm Andy Shaner, as you can see from my name tag there. I am at the Lunar Planetary Institute in Houston. With us tonight is Dr. Georgiana Kramer. She goes by George. She is also with LPI, but she is at home tonight, and she really is not in her backyard. She actually is in a room in her house, but she has a very cool tree painted on the wall. And maybe if you're nice, she'll tell you what that's all about.
I have no
Um, but a little bit about George first. She's a postdoctoral fellow at the Lunar Planetary Institute, LPI. So if you hear LPI, that's what that is. Studying the chemistry and mineralogy of the moon, asteroids, and other planetary surfaces. Her research includes lunar swirls and the magma ocean hypothesis. Uh, she does a lot of spectroscopy, really, is what she does. So most of us, I think, are familiar with learning about spectroscopy as it relates to studying stars or galaxies, things way out there. A little bit of planetary stuff, but George, maybe you could tell us what's the difference between looking at the moon spectroscopically versus studying stars with spectra?
Well, I mean, so first of all, there's a wide, electromagnetic spectrum. So it does somewhat depend on what part of the spectrum you're talking about. But typically, like Hubble, for instance, looks out at the universe in pretty much the visible spectrum, and as humans see it a little bit more, but and it's mostly measuring radiant light or spectra, stuff that is actually is shining out from stars. So when you look at stars or galaxies and such, you're actually looking at the light that they're emitting themselves. And what I look at in particular on the moon is light that is being reflected from the sun. So the moon is it's not radiating its own energy, at least in the visible part of the spectrum. It gets that from the sun shining on it, and then stuff reflects back. So that's the difference.
Okay. Um, so so you're a planetary science or a geologist by training. So why did you decide to look at light instead of rocks?
Um, well, when I was an undergrad, I was interested in remote sensing right away, and I got to do some stuff through the Hawaii Space Grant, and I really liked it. So I actually went to Notre Dame intending to do that, but my advice, well, not but, fortunately, uh, my advisor, Clive Neal, was not a remote sensing scientist. He was a geochemist and petrologist. So the remote sensing part got like slightly diverted temporarily, and I actually got to learn about that, which is really fantastic and puts some more tools in my belt. But during my graduate career, I actually took on, or rather was given, Brad Jolliffe from Washington University, who became my sort of second advisor, and he taught me the remote sensing side. When I graduated, my first job I got was with Tom McCord in the Verify Institute in Washington State, and he is a spectroscopist and has been for virtually ever. And he taught me real hardcore reflectance spectroscopy.
Okay. Well, thank you.
And I am done.
So, how has spectroscopy, at least with the moon, I guess, has it been done for a long time? Now, there actually has been. Okay, I can answer that question somewhat myself. There was spectroscopy on Clementine of the moon back in the early '90s. How does that differ, if it does, from spectroscopy we do today? What are some examples of missions that have done spectroscopy?
Well, spectroscopy from the moon actually started with telescopes.
Touche.
Mm-hmm. And from telescopes went to a little bit of Galileo, and then en route to Jupiter. And this was followed by Clementine. And the stuff the spectra that I work with now, mostly, at least with regard to reflectance spectra, is from the Moon Mineralogy Mapper, which was a recent mission that was on the Indian mission Chandrayaan-1. The difference between the Moon Mineralogy Mapper instrument and the spectra that come from that and the Clementine one is that they both basically cover the same spectral range, which is visible light and a bunch of near infrared. But Clementine, if you take into account every single band that Clementine had, there was 11. So there's 11 channels across that entire spectral range. With the Moon Mineralogy Mapper, it's 83 bands that globally cover the moon.
Okay. So which parts of the spectrum are I don't want to say the most important, but maybe the most utilized in lunar spectroscopy, and why?
So the parts that are most utilized are probably mostly the near-infrared portion. So this is out of our visible range, and moving towards radiant heat, sort of, but we haven't got there yet. And at about so the visible range, I'm going to start throwing some numbers at you guys. The visible range goes between 0.4 and 0.7 microns, or micrometers. One of the first very important wavelengths that is at around 1 micron. And then there's another important one out at 2 microns. And these are due to mafic minerals, which are a lot of the minerals that make up the moon. So these features are actually, you have this reflectance spectrum. There's this, at all these wavelengths, light is coming back at you. But at 1 and 2 microns, if you have a bunch of mafic minerals, then one or both of these channels are being absorbed. So there's not as much light being reflected back. Since we can't see that sort of thing because it's out in the infrared, we need the spectrometer to do it. Another really, really important wavelength or band is out at about 3 microns. And this has become particularly interesting lately because the Moon Mineralogy Mapper was one of 3 instruments that discovered water all over the lunar surface. And that is due to an absorption that occurs out at 3 microns.
Okay, so water is a big deal.
Water is a big deal on the moon now, even though there's not a lot of water on the moon.
Okay, very good. Well, if some of you have joined us, maybe just within the past few minutes, I want to welcome you to tonight's webcast. I'm sorry, Hangout. Got to get used to saying the word Hangout. With MyMoon and Cosmoquest. MyMoon is used to doing webcasts, of course, but with a different platform. We're using Hangout now, so I got to start using Hangout. Talking to Georgiana Kramer from the Lunar and Planetary Institute. My name is Andy Shaner. I'm with the Lunar and Planetary Institute. And George is talking to us about spectroscopy and studying the moon with spectroscopy. Just to kind of maybe go with something. Well, first of all, has anybody posted any questions? Do we have any questions from viewers?
Not yet, but I'd like to let you guys know if you want to ask questions, you can ask on the YouTube page, on the Google event, on anywhere on Google Plus you're watching this, any of those places I'm watching the comments, and also on Twitter. If you use the hashtag MyMoonLPI, we'll be watching that as well.
Right. Thank you, Nicole. Yes, please don't be shy. Jump in there with any questions you might have. George is more than happy to answer them for you. Okay, so the lunar swirls thing, I really have no idea what this is, and I guess whenever I've tried to picture it, I think of like dust devils. That doesn't make sense because there's no wind on the moon. So, George, what do we mean when we talk about lunar swirls, and how are you looking at those?
Well, I mean, dust devils isn't so bad, but I would say, how about what was that one Warner Brothers character? You know, the Tasmanian devil. That's right, right? And he'd spin around and around, and he'd go like in all these crazy directions, right? Well, if you imagine like the Tasmanian devil, and he went like and he spun all around, and then and he made a trace on the ground. That's kind of like what the swirls look like. So, so lunar swirls are these bright features on the surface, and they are not, well, recently it looks like we're beginning to explain them actually, but for a really long time it really wasn't understood what these things were. They're bright features. They usually have these swirly shapes to them, like yeah, swirly, when you say. And and everywhere there is a lunar swirl, there's a magnetic anomaly. On the moon, there's no magnetic fields in the moon like there is on Earth. You know, or even on Mercury or Mars, or even Mars actually has this remnant magnetic field. But on the moon, it's even less than that, less than on Mars. There's only like a few isolated locations where we have this magnetic field. And every time you find a swirl, you find a magnetic field. So the hypothesis that I favor, I didn't come up with it, but it's certainly one that I have been supporting with the work I've been doing, is that the lunar swirls are caused by these magnetic anomalies staving off the solar wind, or blocking the solar wind from coming down to the surface and turning it darker. It doesn't sound very interesting maybe when I say it like that. There's like a whole lot of other stuff to be said about it, but they're very fascinating. And as I said before, for a real long time they were very mysterious. Yeah. Only recently has this become more and more apparent that this is what's going on, that the magnetic anomalies are controlling what we call space weathering, or they're rather blocking space weathering. And when I say there's been recent work, it's because of all of these satellites that have recently been thrown at the moon. From Japan and from China and from India and America, that we're getting all of this new data, and electromagnetophysicists that do stuff that is magic to me have been able to, look at this data and see these particles and these electrons and these protons and say, wow, they're really acting strangely, and they act particularly strangely at the magnetic anomalies, and wow, what if they're making these weird swirling patterns? And the spectra that I look at suggest the same thing too.
Cool.
We have a question, George, from your nephew Dylan.
Hey, Dylan.
He asks, he wants to know how the discovery of water on the Genesis moon rock will affect what we think about the moon's origin. So can you tell us a little bit about, first of all, what we think the moon's origin story is, and how that might be changing?
The water found on the Genesis moon rock. Are you talking about the new Nature Geoscience paper? Seriously.
That might be it. I don't know.
I haven't read that. If it's this paper, I haven't read that one in completely. I do know that there was some new analyses done on a anorthosite, and they found some few ppm water in it. That's amazing if that's really what's going on. It certainly is possible that we could be measuring water now where we couldn't before, because there's been new instruments and such that can actually detect these things a lot better than they did before. But as I said, I haven't read it. I think that's kind of amazing. Mm-hmm. So we'll see what happens. Sorry I couldn't answer it completely, Dylan. It's a good question, though.
Yeah, yeah.
Well, George, I actually kind of, I guess, just off of what part of the question was, maybe you could tell us a little bit about what the current lunar formation hypothesis is or idea is. Maybe how spectroscopy is helping answer that.
Well, so the basic theory that is that when the Earth had newly formed and begun to differentiate itself into a core and mantle and crust, an object about the size of Mars crossed the Earth's orbit and actually smacked it. And this material went off around and started, this like just little tiny bits of molten material or little bits of rock and dust and such went out and started orbiting the Earth, and slowly this material started coming back together and formed our moon. There has been a lot of talk that this was a very energetic event, and so all of the volatiles would have been driven off by the impact and even the reformation of the moon. So therefore, that's why we don't have all this water in the moon. But there has been some recent analyses on some lunar volcanic glasses and some minerals, apatite in particular, apatite being this one particular mineral that is one of the late stage minerals, or rather one of the last minerals to crystallize. Oh, I skipped that part, I'm sorry. Hello.
That's fine.
Okay, so back up a little bit. Okay, so there's all these little bits floating around the Earth after the impact. And these bits start coming together, and they finally, once they're all pretty much together formed, that happens, I said slowly, but actually in geologic timescale really fast. So therefore, it was also a very energetic event. And so you have this molten, think of like a magma chamber, except take away the crust that's all surrounding it, and you have this magma, basically, ball that's floating in space and orbiting the Earth. And now this starts to cool. Now, if you have a perfect magma chamber that is made up of this same kind of material, and you were able to cool it slowly and watch the crystals that are forming, there's a particular sequence of crystals that would fall out of it. You'd start with olivine, which is, its gemstone is known as peridot. And then you'd be followed by pyroxene. I don't know what its gemstone is called. And one of the last major minerals to form is plagioclase. Olivine and pyroxene are both pretty dark minerals. Pyroxene pretty much black, but plagioclase is usually bright, even white. And plagioclase actually floats to the top while olivine and pyroxene sink towards the bottom. And you wind up getting this plagioclase crust all over the moon. A lot of the moon's surface is still covered in that, and that's why the moon is so bright. Why it reflects so much light back at us is because it's mostly covered in this. But there was still some more impacts that were occurring on the moon even after the crust had formed. And they were huge. And they made like the eyes and the nose and stuff in the man in the moon, or from what I see, it's the squirrel's head and body, tail, and he's feeding a poodle, and it's the poodle's head and the poodle's body and the poodle's tail also. These are these dark spots, and they're called mare. And they were basically these huge depressions in the bright plagioclase crust. And they were depressions, and they got filled with melt of that olivine and pyroxene rich material that was deeper down. Filled it up, and that's how you get the mare. So I was talking about the water, wasn't I?
Oh my God, I just learned so much now about the dark spots in the moon, because you always talk about them as, yeah, that's the impact left over, but I had no idea the mineral names behind it. That's really cool.
By the way, George just traced out about half a billion years of the moon's, or first years of the moon's life, by the way. So now if you just go through the next 4 billion.
How time flies.
That would be awesome. No, just kidding.
I remember now what your question was. You were asking me how spectroscopy has changed this picture, right?
Or how it's aided in it, yeah.
Or aided in it. Okay, yeah, that's right, aided in it, because it hasn't changed the picture. But there's kind of some nuances to this story. So I said, there was olivine and pyroxene, and then plagioclase up on top. Well, there's different kinds of pyroxenes, and there's going to be some mixtures of the pyroxene and the plagioclase because of impacts that are occurring, and then there's more basalts that have filled up in these giant basins, but then impacts into that, and that's mixing with the plagioclase. And anyway, so you get these like more complex layers of the crust and such. And people have modeled these things, and they said, well, look, if we had this giant molten magma ball and it crystallized slowly and it did this sequence and then it was impacted a lot and then it mixed like this, then we should have these particular things. And the crust should be this deep, and the source of the Mare basalt magmas should be this deep, and so on and so forth. Well, the Moon Mineralogy Mapper in particular is a really great spectrometer, and we were able to look at some of the more specific compositions of these different minerals, like some of the like subsets, if you will, of pyroxenes, different chemistries of pyroxenes, and plagioclase too. And we are seeing in some of these giant impact basins that were not filled with Mare basalt. In the center of them, sometimes an impact basin or an impact crater will be so big that it hits and it doesn't just make a bowl, but you actually get like a rebound, sort of like if you drop a pebble into water and you get this like rebound effect, but then it freezes because it's rock. Well, this when we look at these frozen center points of the craters and such, we're seeing some minerals in there that, well, they're plagioclase or pyroxene or olivine, but they're not where we think that they should be, because people who study impact craters can say something about, well, we think that, you know, that center point, for instance, is going to come from this particular depth, and other people have modeled, well, we think these minerals are going to be at this depth, and then the Moon Mineralogy Mapper looks at it and says, wait a minute, it's saying something completely different. So that's how it's sort of helped and changed. It doesn't always say that it's completely different.
Excellent, thank you.
It's interesting when it does.
Yeah.
So we actually got a bunch of questions about the swirls, actually, so I'd like to go back to that for a minute. Tom Nath asks, has there been any photographic changes over time for these swirls?
That's a really good question. There have not been. I guess I would say that I'm not surprised, because the magnetic field, we don't think the magnetic field would be moving, right? We think that it's basically, there was some event that I have no idea what it would be, that made this magnetic anomaly occur, but it's probably frozen in the rock. So it's kind of like you put some suntan, right? Like, look, you take a suntan lotion and you put it on, wait, there's my arm, right? And you put like a figure 8 on your arm, right? And then you go out and you get a sunburn. Except where the figure 8 is, it's not going to be sunburned. It's still going to be really bright, as your skin was before, if your skin was bright. That's kind of like what is going on with the swirls. So, except that the suntan lotion is actually a magnetic field, and it's not allowing the sun's radiation to get to it. So the material there, which was bright to begin with, is just continuing to stay bright.
So Nathan Reynolds asks, in relation to this, and I'm curious too, do these magnetic anomalies, do they block some kind of physical breakdown of the minerals and the rocks on the moon?
Yeah.
Is that what's causing the color change?
Yeah, so that's actually what I was able to contribute to this story, is that the solar wind is throwing like protons, okay? It's throwing helium ions, or excuse me, well, helium, yes, but mostly hydrogen ions at the lunar surface. And these protons can sputter and or chemically alter the surface. In particular, when it interacts with iron oxide, like that you have in mafic minerals, like pyroxene and olivine and even plagioclase a little bit, it will actually, either through sputtering or chemical reduction, cause the oxygen and the iron to separate from each other, and maybe the oxygen and the hydrogen become friends and then go somewhere else, and then you get OH on the surface, another story. But anyway, the iron that's left over winds up having no charge to it. So basically you have a little atom of iron metal, And then the thing is that this is occurring so very much that you actually wind up having these blebs of iron metal. We call it nanophase iron, and these have been measured in lunar soil samples that have been returned. Nanophase iron has the effect of taking whatever reflectance spectrum you have and causing it to darken a lot. There's very specific things that the occurrence of nanophase iron winds up doing to the spectra, and this is related to its abundance. It's also related to the size of the nanophase iron particle. If it's large enough, then we start calling it microphase iron because it's not nano anymore. And those have different effects on the spectra than nanophase iron does, the microphase versus nanophase. So I was actually able to observe that at these lunar swirls, the microphase iron actually didn't seem to really be created. Maybe there was a little nanophase iron because you still get micrometeorites that impact, and they're not influenced by magnetic field. So you have this, there's a bit of nanophase iron around. But what's really interesting is that right next to the lunar swirls, and particularly in between them, there's these really dark areas that wind between them. And one question is, well, are they just, an albedo contrast difference because you have like a bright area and then another bright area, so in between it looks dark? Or is it that they're actually really darker? Well, I was able to show that they're actually really darker. And so what it does appear to be going on is that the solar wind tries to come onto the lunar swirl surfaces, magnetic field deflects it, and the ions wind up funneling down into these dark lanes. And they start weathering really, really rapidly. Wow. So you get a lot of this microphase iron, these large things that have, as I said again, this particular effect on the spectra, which is making it really dark.
Cool. Nick Azer says, sorry, pronunciation, says it sounds useful for astronauts. There's less radiation coming in. There's less solar wind particles hitting at that spot. About how big are these areas? Can you put a person there or a building or?
Yeah, certainly you could. I've heard from, I really don't know how much benefit it would be to people, or it's not going to affect photons. So for instance, like galactic cosmic rays, gamma rays and such, which are really what puts people in danger, it doesn't have any effect on those things.
Yeah.
So it will have effect on these ions, but I think mostly your spacesuits or your buildings are going to be blocking that too.
Okay.
So from what I understand, it's not maybe that useful for astronauts to work in, although it would be interesting for us to get samples from them.
Gotcha. And one more related to the swirls from Chris Rand. The magnetic anomalies that stave off the solar wind, is that sort of like a really small localized version of our northern and southern lights of the aurorae on Earth?
Well, I guess kind of no. So yeah, hold on a second. At the poles, the magnetic field is like funneling down these the solar wind, and it's actually causing these electrons to strike the atmosphere with a lot of energy, and then you wind up getting these lights that are created. So I guess because the moon lacks an atmosphere, then it's not really related.
Effect. Right.
Yeah, but at the same time, they are funneling down these the ions into the dark lane areas. So were there an atmosphere, then yeah, then that could be occurring.
Cool.
All right, those are some great questions. All right, thank you, George, for those replies. So earlier you were talking about there's all these spacecraft buzzing around the moon right now.
Well, now there's only one. Oh no, I'm sorry, that's not true. I keep doing that. There's I guess kind of like 3, but really it's just 2 missions.
Right. Well, okay. I just meant the physical spacecraft, but okay. Do you have any like wishes for future missions to fly spectrometers, and what kind of things should future missions be looking for with spectroscopy?
Oh no, we're all done. I'm just kidding. Oh my gosh, I'm just kidding. No.
You'll never ever hear a scientist say that. Seriously.
No, we're so far from done. Yeah, the whole the whole idea that, oh, we've been to the moon, we've been there, done that, it's time to go somewhere else is just absolutely absurd. But we've never been to the far side, like, at all. But anyway, so I mean, I think that what is really important is for us to go get more samples. And I actually am trying to put forth a huge argument as to why I know a great place actually at a lunar swirl that we could go. We could get South Pole Lake and Basin samples, which is the largest impact that was on the moon and very ancient. And we could also be sampling at a magnetically protected region, so maybe sampling what is like fresh soil, and then right next to it, just like, I don't know, a foot away, we can get ones that are actually really old and mature. What was the question again?
What kind of future missions, like in terms of spectroscopy, what kind of future thing would you like to see done with spectroscopy?
Oh yeah, I'm sorry. So the Moon Mineralogy Mapper was just an absolutely incredible mission. Instrument. The Chandrayaan space mission was an incredible mission. Unfortunately, it ended about I think about 2 years before it was supposed to. It's amazing. It actually was able to keep going when it should have not been able to any longer. They really did some amazing stuff, the engineers on that. But at any rate, it would be great to have another Moon Mineralogy Mapper go back. And as I said, it did map virtually the entire moon. It's missing, I think it was 96% or something like that. But it's actually missing data in this one of the greatest swirl locations, which is just like it hates me. But it would be great to do that. And I do know that the technology is advanced now that they can actually have a spectrometer that goes out to at least 3.5 microns. And so one of the biggest things that came from that instrument was the discovery of water all over the lunar surface, and also that it varies with the diurnal cycle of the moon. So, like when a particular patch on the moon comes into the the sun's light, then any hydroxyl or water that's attached to the surface gets driven off, and then as it goes into the night side, it sticks because the thermal energy is reduced. But the wavelength range of that instrument went out to 3 microns, and that's like the middle of the water feature. So we don't really know what the other end of it looks like. We don't know how deep it is. It would be close to impossible for us to quantify the water as a result of that. So it would be really beneficial for us to go back, do complete coverage with higher spatial resolution and higher spectral resolution, and having that continued spectral range would be absolutely important, especially for our continued efforts to go to the moon and colonize it.
You just said something about going farther out in the spectra because you don't know how deep it is. Does that mean you can look farther down on the surface if you have a wider range of spectra?
Yeah, I'm sorry, that wasn't right. So when I say deep, I meant the absorption feature. So if you think of the spectra, there's all this light coming at you, and if you could see that 3 micron out to 3 microns, there would be light coming out at you at like 2.6 or 7, and then there might be light coming out at you at like 3.3. But in between 2.6 and 3.3, it would decrease. It wouldn't be as bright in that area. So that's if you plot this on like with reflectance versus wavelength, you wind up getting this absorption. We call it an absorption feature. You get this trough. So that was the depth of the band I was talking about.
Okay. Well, thank you. Nicole, are there any other questions people have submitted?
Yeah. Nick Ezer wants to know where are the best swirl locations? Which one's the coolest?
So Marian Genii, which is in South Pole Lake, next to Oppenheimer, is where I sort of cut my swirl teeth.
Sounds like you said squirrel teeth. Sorry.
The lunar squirrels, yeah. It's one of the most fantastic swirl areas, and it has one of the strongest magnetic anomalies too. And Rainier Gamma on the near side is one of the most famous swirls because it's well, it's the most prominent one that's on the near side, so it's actually been observed for a long time. But the one that I've been dying to like really pay attention to, and the one where there's some data missing from Moon Mineralogy Mapper, is at Mare Marginis. There's a crater into the that's just north of Mare Marginis. Mare Marginis is on the eastern limb of the Moon, and just north of Mare Marginis there is a impact crater called Goddard A, and it's a very fresh impact crater, and emanating from that impact crater are lunar swirls. And it kind of looks like you have these really wavy, trippy looking ejecta rays coming from Goddard A. And to some extent, yeah, that's true. But it's more than that. It's more complicated than that. I mean, Goddard A provided all this bright material to be thrown down, right. And then the magnetic field provided this magnetic field to keep the solar wind from darkening it.
Cool. And Chris Rand asks if can we drop a moon rover with a spectrometer on it to do some of these experiments? Would that help?
I guess putting a spectrometer onto a rover would be good for looking at some of the more detailed mineralogy that we're seeing, and I would actually prefer that something like that be thrown at some of these impact basins that haven't been filled with Mare, like Mare Oriental or Schrödinger, which is in the South Pole, because there's some really, really interesting mineralogy there, and that's what is a spectrometer's strength, is seeing the minerals.
Cool. And actually, I have a question. Would you personally put down the spectrometer and pick up a hammer if you had a chance to go?
Oh yeah.
Actually do field geology.
Yes. Yes, you who hire astronauts. I volunteer.
Go. Okay. Cool.
George is pretty deadly with a hammer, though. Not in the real sense of deadly. I just spent a couple of days with George at Meteor Crater, walking around that thing, and it was interesting. So George gets to travel around quite a bit. In fact, she recently went to Japan and spoke with some scientists there. And the best part about her trip was what she brought back. She brought back these wasabi-flavored Kit Kat and green tea flavored Kit Kats. I gotta tell you, the wasabi was not bad. It was pretty good. The green tea, really couldn't taste it, but it was pretty good. So I guess a real question in that or something is what did you talk about over there in Japan?
Recently, I've been looking at Mare Frigoris, which is this elongated sort of feature above Mare Imbrium. So it's on the lunar near side. I call it the eyebrow of Imbrium, but I only call it that to myself. So it's okay. Again, it's an elongated feature, so its origin is is unknown. You know, why would it look like this? But anyway, there's definitely this depression that is occurring there that got filled with Mare basalts. And so I've been using small impact craters. I mean, small like less than 5 kilometers. I'm looking at impact craters that have not penetrated the Mare basalts and gone like all the way through to beneath them, but I just want to actually get at the composition of the basalts themselves. So ones that aren't that deep, that they would go all the way through, that are sampling the basalts, and I'm focusing on the ones that are fresh, so that I can see what the composition of the fresh basalt is. And this is of interest because the moon is covered with 4 billion years worth of soil development, and this stuff is meters thick. And it's basically the composition of the entire moon all mixed up together and thrown onto the surface. Not exactly, but it's definitely not telling us exactly what the fresh basalt composition is. So that's why I've been using these small impact craters. So I presented the work that I had done there and the findings.
Oh, right. And how was that received over there?
It was received well, I think.
Well, I'm going to guess so if you were invited to go talk about it.
So I was invited to talk about it, I guess mostly because this was a symposium for the Selene or Kaguya Japanese mission to the moon, which was a couple of years ago, a few years ago. And they, one of the conveners wanted to put together one that, where people were looking at these different Mare basalts, like from like Mare Imbrium or Crisium, or all these different Mare basalt characterizations or maps or whatever people have done. And I'm the only one who's done any work on Frigoris in a really long time, so that's why I was invited.
Well, very good.
Cool.
Any questions from our audience?
We have more swirls questions.
Yeah!
We got people excited about this. This is great. Sylvan Westby asks, is there a hypothesis for the formation of these magnetic anomalies? Could they be remains from a time when the moon had an active magnetic field while it was molten?
Yeah, that's a very good observation, a good hypothesis yourself. So yeah, it's the kind of, I guess I would say, leading theory that I don't disagree with, at least. So I guess I'll present them both, even though one of them is just not what's the truth. Okay, well, I'll start with the one that's not the truth. Before the most recent missions, one of the other ideas about what the lunar swirls were caused by was a comet impact. So nothing to do with the solar wind being staved off, completely ignoring the magnetic anomalies, well, for the most part ignoring them, but yeah, that a comet came and impacted, and it was actually, it would be a fresh or a recent impact. And because of the comet being icy and having a tail and all of its stuff, it left this trippy little pattern onto the surface. Mm-hmm. Eventually, when I guess people started, pressed the proponents of that hypothesis, hey, well, what about the magnetic anomaly? They put forward an idea that as the comet's actually approaching the surface, an atmosphere is basically generated because the comet has a coma around it, and pressures get developed, and you wind up, you have a plasma, I don't know, some physics stuff that I don't really understand completely, but because this plasma winds up being generated, a magnetic field gets generated, and that's what got put down the magnetic anomalies.
Okay.
Any of the plasma physicists that I've spoken to about this tell me that it's not a good explanation, and they don't believe it, and I believe them because I don't know any better. But now the other hypothesis was put forward by Lon Hood, and I believe that the first time he put this forth was in 78 or 79. He noticed that most of these lunar swirls were antipodal to major impact basins, or rather the more recent major impact basins. So there's one on the opposite side of the moon from Mare Imbrium, Mare Crisium, etc. And pretty much the only one that didn't follow this idea was Rainer Gamma, which is not antipodal to anything, but let's put Rainer Gamma aside for now. He had a different explanation, but it doesn't matter. So if indeed these magnetic anomalies are caused because they are antipodal, it is that there's a major impact that occurs on, like, let's say with Imbrium, and let's say at that time that either the moon had a magnetic field, sort of like the Earth does, or apparently the interplanetary magnetic field would have been enough that when this impact occurs, you get this, this huge ejecta and shock waves that go around, and you get this plasma that forms, and it actually winds up pushing on the interplanetary magnetic field. I'm probably butchering this hypothesis, but and kind of like bends it over on itself and does some sort of magical stuff where it actually concentrates it and makes it stronger than it was just blown by the moon. And this gets recorded in the ejecta that winds up meeting at the other side of the moon.
Wow. I'm
probably going to get a lot of emails from people.
from
how could you say it like that? Doesn't make any sense.
I just want to point out that magnetic fields are magic.
Yeah, they're...
Not really. Okay. Marcus Bryers asks, we're talking about lunar swirls. Are there Earth swirls? Is there anything analogous to this on Earth or anywhere else in the solar system?
Well, it's probably like somebody, and I forget what his name was, I brought up before. Maybe the Van Allen, not the Van Allen belts. I'm sorry, but the Aurora Borealis and Australis could be maybe the closest sort of thing to a swirl, but they'd be transient. So because the Earth has this giant magnetic field, it's going to keep, I mean, it's just everywhere. So it keeps the solar wind protons out. They're not allowed in, so they can't do the kinds of weathering, at least in isolated patch locations. And so it's the one thing that we're still investigating, we being the planetary science community, is do the shapes of the swirls actually, are they actually basically outlining what the magnetic field pattern looks like right at the surface? Because all of the measurements of, excuse me, all of the measurements of the magnetic fields are from spacecraft altitude, and we don't know what the magnetic field is like literally at the surface. So that part is not exactly known. I think it's a good hypothesis that that is what's going on, but I certainly couldn't begin to explain how a bunch of magnetic dipoles thrown across the lunar surface would make these particular shapes.
Yeah.
Would it be possible to observe something like this on one of the Galilean satellites within Jupiter's ginormous magnetic field?
Let's see. From Jupiter. I don't know. Does Jupiter throw protons and such? I mean, specifically, with at least spectrally, it's going to require that there is something sputtering iron oxide and causing the creation of nanophase iron and such. So, or basically, that if there's a magnetic field that is keeping X from causing the surface to darken or weather over time. So I'm not really sure what exactly what Jupiter's throwing at their at its moons. I think that something like this could be occurring on Vesta, although nothing was found. I think that the asteroid belt could be a place that this could be observed. One of the major things that came out of the work that I did on the lunar swirls and the spectra was that I concluded that the solar wind was very much the dominating space weathering agent on the lunar surface. So the space weathering agents being the sun's solar radiation and micrometeorites. Because micrometeorites can impact the surface, and I mean micrometeorites like dust. Impacts the surface, can sputter, can cause the reduction of iron, and so on and so forth, so you can get the creation of nanophase iron from it. But they're not affected by magnetic anomaly. And so because these lunar swirls, which by using other means I was able to show are actually just as old as the surface right next to them, where it's dark or where nothing's happening at all. It had to be that the solar wind was the thing that was causing the space weathering across the moon, elsewhere where there's no magnetic anomaly. Had to be the thing that was really dominating it. And out at the asteroid belt, there might actually be a trade-off. It might actually occur that that is far enough away from the sun that micrometeorites and the solar wind are about equal. But we should be throwing more instruments at the asteroid belt, looking at the new dwarf planets and such.
Yeah. You hear that, Vesta mappers? I know some of you are watching. Look for swirls in your images now.
They'd also tell you if there's a magnetic field.
Yeah. Yeah. That would be pretty cool. Tom Nath asks about have you or anyone working on this looked at old lunar transient phenomena sites?
I haven't. I do know that there's people that have been doing that. As a matter of fact, at this symposium I was at in Japan, I remember that there was a talk about I guess it was the one at Aristarchus, I think, where I think that's where there's the most amount of these lunar transient phenomena have been identified. And it had something to do with isotopes and measurements of radon isotopes, and I don't really understand. So So I'm not looking into that, but yeah, people are, and they're doing it with some of the new data that's coming out of these instruments. And I'm trying to remember what instrument he was using, if it was like gamma ray or it was, no, it couldn't have been, it must have been some sort of a particle detector.
Mm-hmm.
Alpha particle detector, that's what it was.
Cool. Okay.
Is there any more from the?
No, I think that's it right now.
Okay. All right, great. Well, we're actually, I guess maybe we're about 10 minutes out from needing to wrap this up. But tell me, George, what's your favorite moon conspiracy hoax or hoax claim? Yeah, I went there.
Nazis.
Oh,
Nazis
right.
on the moon.
Okay, you'll have to explain that a little more for me.
I don't know. I haven't seen the movie yet, but I do have
Wow.
a copy of it. I'm just waiting. I actually would. I think we should make it an LPI event. It's
Yeah, well, we'll talk about that.
the movie's called. I think it's called Iron Sky, and it was put out. It's a Finnish movie, but it's in English.
Oh
And
yeah.
it was. I can't think it came out last year, and it's about Nazis that were hiding out on. I think on the far side of the moon, but then they come back to take over. That's awesome.
So they didn't age?
I can't answer that. I'm not allowed. No.
Is this on Netflix?
I hope so. I don't know. I'm not sure.
Okay, I'm gonna have to check this out.
Yeah, actually, now that you mentioned it, I think Nick, who's with us tonight, I think he may have blogged about that once or twice for MyMoon, so maybe we'll just have to go back and look that up.
Wow.
Okay, very good. So Nazis is your favorite.
Nazis
Okay,
on the moon. Yeah.
maybe that'll be my new favorite one after I learn more about it.
I mean, it's just a movie, but it could become a conspiracy.
Oh, I'm sure it is. I'm sure there's a website.
George will find a way, or she'll find the website.
Or I'll make it.
All right. Well, is there anything else from our audience tonight?
Just a "You Are Cool" from Michael Jobin on YouTube.
Wow, thank you, Michael.
Oh, and several people saying yes, it is on Netflix. I know what I'm watching tonight. Do you have any last thoughts or comments, George, before we sign off?
Well, mostly I just want to thank everybody for coming. It's awesome. I'm glad you listened. I'm glad you guys think the swirls are really cool, and that you support planetary science. It's fantastic.
Cool. Thank you so much.
Well, thank you, George, and thank you everybody for joining us tonight, and thank you, Nicole, for kind of running some of the things on the
Analog lower third.
right. For running the behind the scenes for us tonight. And again, thank you everybody for your great questions and your comments. This is a second web or Hangout in a partnership between MyMoon and Cosmoquest. So check out MyMoon at mymoonspace.com, and be sure to also do your moon mapping and your Vesta mapping and look for those
Lunar squirrels!
very good lunar squirrels.
We have our own squirrel in honor of my moon. So.
Yeah, if you go to MyMoon and you see references to squirrels here and there, I'm not going to say it's all going to make sense.
I don't get it. Yeah, I don't get it. I have it on my desk, and I have it.
That's where it comes from. So make sure you go to your moon mappers and was it Vesta or asteroid mappers?
Asteroid mappers. Yeah, we currently have Vesta project. And the moon mappers from all the LRO data. You guys have marked over 1 million craters within a year with us on Cosmoquest. So thank you, and keep going. The first science results should be getting published soon. They're going back and forth with the reviewer, so we've got that coming out.
Very good. And whoever sees a swirl in Vesta mappers, make sure you let George know.
Me.
Call her, yes. Post it on the forum or tweet us. Yeah, that would be so cool.
All right. Well, thank you again, everybody. Our next hangout will be on March 13th. At least a MyMoon Cosmoquest hangout is on March 13th with Catherine Niche from the Applied Physics Lab at Johns Hopkins. So be looking
Ask her
out.
about lunar swirls.
Ask Catherine about them? All right.
Sweet.
All right. All right. Well, we look forward to seeing you all then. So until then, good night, and thanks for joining us.
Thanks, everyone.
Night.